Yes. And I think, yeah, let us begin. Um, so for the first journal club, I think it would be good if we start from linear algebra. So there'll be a lot of very basic stuff if you have already gone through like basic quantum mechanics. But if you have not, then so everyone can see my screen, right? Just to make sure. Okay. Uh, so the first journal club would be to cover all the linear algebra needed for the subsequent discussion. So if you don't understand any of these quantum mechanics, is fine because most of the knowledge will be coming from linear algebra perspective. Okay. So the first thing we need to know is basically what is a vector. So you can consider a vector as an n tuple of entries. So that can be represented as a column vector. So each of these entry right now, I did not specify what it is. So it can be a real number or it can be a complex number. But for our purposes, we basically only focus on complex vector space. So this is a space of all complex vectors. And usually the notation will be written as, if you typeset using LaTeX, it will be math BB C. So the dimensionality of your complex vector is n dimension. So what you need to know for vector space is basically you have two operations. So you can add up the vectors and you can do a scalar multiplication. There are a lot of more detailed mathematics, but I don't think that is necessary beyond just knowing these two operations at this point. So, uh, and by the way, if you have any question, you can just unmute yourself and ask. Uh, Unfortunately, I'm multitasking, like recording and then doing the presentation. So I don't think I have time to look at uh, the Google Meet. So you just need to know that right now your vector space has these two operations, the vector addition and scalar multiplication, and that's it. Over here, I mentioned a little bit of what is a qubit. At this point, what you need to know is that a qubit is basically a quantum motion of a classical bit. So we usually say that a qubit is a superposition of the 0 and 1 states, but you don't need to use the word superposition. So in the linear algebra terms, you can just say that it is a linear combinations of two bases. So the first basis is 0, the second basis is 1. So if you don't want to use the 0 and 1 states, and if you want to stick with the vector space notation, what you can usually write is something like this. So this will be your basis states. And then basically you can see that your quantum state for the qubit basically is complex vectors. Okay. So then if you don't want to, if you want to avoid for now, what is a qubit, what is a superposition, and all that, what you can say is basically you are considering a complex vector space of dimension 2, and the vector inside will be, let's say, given by something like this. Uh, V0 and then E0 plus V1, E1. So this will be your basis states, or just basis at this point. So this is one possibility that you can describe what is qubit. But I assume everyone here knows a little bit of quantum, so that's why I put some leeways here. So basically, qubit is written by something like this. So this is what we call as the bracket notation. And over here, I also mentioned that your psi naught and psi 1 are probability amplitudes, and they are generally a complex number. So this notation over here is what we call as a ket vector, and it can also be represented as a column vector. So if you write it in terms of a column vector, then it will be in this form, and this will be in the two-dimensional complex vector space. So ideally, we can define further what is the matrix representation for your basis states. So usually we use computational basis. So the 0 and 1 are represented by these column vectors. So one thing for you to note that is that these two ket vectors, they are orthonormal to each other. What it means is that it is orthogonal, and if you perform the inner product, which I will explain later, that will be equals to 1. So that's the definition of orthonormality. We also have what we call as the dual vector to the ket, and we call that as a bra vector. So the bra vector is denoted by something like this. And over here, the bar here represents complex conjugate operations. And you can see that the matrix representation is basically a row vector. So the bra for 0 would be a row vector like this. The bra for 1 will be a row vector like this. So the next thing is that we also know that the state vectors of a qubit, the state vector of a qubit, they basically lives in the Hilbert space. If right now this is too complicated for you to understand, you don't need to use the word Hilbert space. Hilbert space basically is just a vector space with inner product. So this is how you define Hilbert space in a simpler way. You just mentioned that it is a vector space with inner product operations. So for one qubit, basically it is just C2. And like I said, you have an inner product operation, which corresponds back to the definitions of orthonormality. So you can perform the inner product through a combination of bra and cats, and you can just write as a matrix form the row vector multiplied with the column vectors, and when you multiply them together, it gives you a real number. So right now we don't want to look at what does this number means. There is also another product called the outer product. So sometimes this outer product is also called a tensor product. So I will define what is a tensor product next. But essentially, outer product is just your cat multiplied with your bra. So if you do that, then you will basically see it is a column vector multiplied with a row vector, and it will give you a 2 times 2 matrix. So we also know that we have these 4 very important matrices called the Pauli matrices. Um, Usually the notation is sigma 0 until sigma 3, but I also use I, X, Y, and Z, and these are the matrix representation. What is more important is how they multiply together. Of course, if you read the textbook or the literatures, you will see like the anti-commutator of your Pauli matrices and your commutator for your Pauli matrices. So those are not important at this moment. So when it is important, I will introduce that properly. But for now, what we need to understand is how they multiply together. So when x multiply with y, you get iz. When you reverse the order, you get a minus sign. So then you see that your x, y, and z operates like a cycle. So as long as you multiply according x, y, z, you get the next one with multiplication of complex, the imaginary number. Zx, you get y. And if you reverse the order of this cycle, then you get a minus sign. So that's how you memorize this. And the last thing is that if you multiply xx, yy, and zx together, you get identity. So this is what you need to know. So Pauli matrices, they are traceless. Traceless means that when you try to sum the diagonal elements, they are equal to 0. Of course, when I say that, this does not count. You only look at the sigma 1, sigma 2, and sigma 3. So the reason why I include sigma 0 as the so-called Pauli matrices, uh, maybe I will talk about that in a very late presentation. But for now, when I say Pauli matrices are traceless, it only refers to sigma 1, 2, and 3. So this is one of the property. The second property of Pauli matrices is that it is also Hermitian, meaning that the conjugate transpose is equivalent to itself. So if you don't understand what is conjugate transpose, let's say A is your matrix, you perform complex conjugation, and then you perform a transposition that is equivalent to conjugate transpose. And if your matrix is Hermitian, it means that after you perform the conjugate and transposition, it goes back to itself. So you can demonstrate, like, for example, sigma 2. So you have 0 minus I, 0. So I can perform the conjugate first. So I get 0, I minus I, 0. So this is after the conjugation. And then I perform the transposition, and you will see that it is just sigma 2. So Pauli matrices are also Hermitian. So now if you already do some very fundamental quantum information on quantum mechanics, you probably have seen that we have 3 different sets of bases. The computational basis that I introduced just now. The second one is the plus basis and the minus basis, and the plus I and minus I. So these 3 sets of bases, they actually corresponds to the eigenvectors for each of the Pauli matrices. So Pauli matrices, generally they have 2 eigenvalues. If x, for x, Pauli x, your eigenvectors are plus and minus. And if you add on plus, you get a positive 1 eigenvalues. If you add with the minus, you get minus 1 eigenvalue. For y would be plus I and minus I. For z would be 0 and 1. So you can check all of these independently by yourself and verify that this is true. You will also see that for x, y, and z Pauli matrices, they can also be formulated by outer products. The way to do it is to look back at their eigenvectors and formulate this kind of summation. So for z will be 0, 0, minus 1, 1. For y will be plus I, minus with minus I. For x will be plus minus with the minus. And from 21 until 23, you can actually see why 18, 19, and 20 is true. So like for instance, x with plus is actually this acting together. Sorry, there should be a plus. So when you multiply things inside, you find that this is orthogonal to each other. So this cancel off, and you are just, and then this is equals to 1. So you are just left with the plus. So you can prove 18 until 20 using 21, 22, and 23 actually. So previously, we also mentioned that the bra is dual to the cat. So now we look at the dagger operations, which is a conjugate transpose. You can obviously see that when you perform conjugate transpose on your cat, you get your bra, which is a dual vector. Some of the operations for or the properties for conjugate transpose is that if you have two matrices A and B, when you multiply them together and do a dagger operation, it will becomes the reverse version, and then you just put the dagger, B dagger, A dagger. So because of this property, when you have some operators operating on your side, and then you put a dagger, is actually equivalent to your bra, and then you have an action on your dagger. So this is important later on for the next discussion, I guess. If it is a plus sign between A and B, then you just separate out the dagger operation without any problems. So using this fact, you can show that Pauli matrices are Hermitian. How do you do that? You look back at equation 21, 22, and 23. So for example, if you want to perform X dagger, so it will be, oh, sorry, this. And because of this property, so you basically can write something like this. And then the next thing that you need to do is, this is considered a multiplication. And you know that AB dagger equals to B dagger, A dagger. So when you switch the sign, you find that you get back something like this. So you can repeat the same step for equation 22 and 23 to show that they are Hermitian. Next property is that a matrix is unitary if U dagger equals to the inverse. So then because of equation 14, this implies that your X is actually self-inverse, because when X multiplied together, you get back identity. So because X, Y, and Z are self-inverse, that's why Pauli matrices, they are Hermitian, and then they are unitary. So next thing, we go to the tensor product that just now when we define the outer product, I also mentioned that this is also called a tensor product. So it depends on how you define what is the outer product. For all the subsequent discussion, this is how I would define outer product. If you refer to other sources, they have different ways to define what is an outer product. But essentially, what is a tensor product is you can check this when it is matrices. It is just a canonical product. So how would you perform a canonical product? Basically, if let's say your matrix A is given by this, your matrix B is given by this. So when you perform the tensor product, what you would do is to take um, the first element of matrix A, and then you sort of like just write down the matrix, the whole matrix for B, and then you multiply term by term inside. So then you will get A11, B11, A11, B12. So you can see that this is a block matrix kind of structure. So this is basically A11 multiplied with the whole matrix B, A12 multiplied with the whole matrix B, and so on and so forth. So in general, if you have A tensor with B, they are not equal to B tensor with A. This is in general. Of course, you have specific cases that they will be equal, but generally speaking, they are not equal. So why is this important? This is important later on. Let's say if you have three vectors, sorry, there's something missing here. Uh, let's say you have three vectors. So two of the vectors coming from the vector space V, another vector coming from the vector space W. So the way you perform tensor product just by your looking at the vectors without expanding into the matrix representations is very simple. You just assume that this is a multiplication, and the way you expand into that is just like how you would do multiplication. So it's V1 tensor with W, V2 tensor with W. So this is how you would write it. For physicists, usually we try to skip this. So we just write something like this. So later on, when you see, let's say 0, 0, when you see something like this, it actually means 0 tensor with 0. So similarly, if you have W tensor with V1 and plus V2, so then it's the same thing. Take it as a multiplication, and then you will get WV1, WV2. So over here, you can see that basically you can see something like this. They are not commute. So A tensor B is not equals to B tensor A in general. So one thing that is quite important is that if you have an operator A, X, which is acting on the vector space B, and then you have another operator B, which operates on the vector space W, then so obviously your V1 is coming from the vector space V, your W is coming from the vector space W. So A has to be acting on V, B has to act on W. So when you have this kind of structure, so the operations would be uh, individual by individual. So A will act on V1 and then B will act on W, and then you put the tensor product together. So this kind of operations is what we call as the local operation. It is local operations because uh, A only acts on the vectors from V, B acts on the vector from W. So this is a very interesting question that I took from Nelson and Chuang. So if let's say the Hadamard operator on 1 qubit, you can write in this way. Show that your tensor product of Hadamard is equivalent to this summation. So probably I will just give like 10 minutes for you guys to try before I go to the solution. I hope you guys try it. This is a very common trick for some of the quantum algorithms, especially like what is that one? The George algorithm. I think they basically use this trick. So if you have two operators doing the tensor product, sometimes they write this. So this notation is particularly useful when you are doing the tensor product n times. So then you don't need to write tensor product all the way. So sometimes people use this notation. So the general equation for this, which is given by Nelson and Chuang, is basically this x, y, and then minus 1, x dot y, x, y. So he did not mention what does it mean by x dot y. So x dot y basically is you take your x as a column matrix, x1 until xn. So y would be another column matrix, y1 until yn. So x dot y basically is the inner product of x1 until xn with y1 until yn. Over here, I just want you to do Hadamard tensor 2 times. So that's why I just write the whole equation out. So the way for you to do it is first doing the tensor product. So this is the first h, this is the second h. And then you write down all the possible multiplications out. So now you see that you have this half term, which I write down. So the way for you to write this summation is by looking at your terms inside. So you have 0, 0, 0, 0, 0, 1, 1, 0, 1, 1. These are all positive. When you look at the 0, 1 version, this is positive. This is positive. These two are negative. When you look at the 1, 0 version, these are positive, positive, negative, negative. And then the 1, 1 version, the middle ones are negative. So what does it mean is that you must have minus 1 phase coupled with this kind of inner product structure. Like for instance, if it is 0, 0, no matter 0 multiply with the 0 over here, it still gives you 0. So minus 1 to the power of 0, it gives you a positive 1. So 0, 0, no matter what you multiply, you get a plus sign. 0, 1, when you multiply with 0, 1. So let's look at this negative sign. So x would be 0, y1 would be 0, and then y2 would be, sorry, x2 would be 1, y2 would be 1. So over here you have minus 1 to the power of 1. And then this term coupled together is 0, 1, outer product with 0, 1. So you look at all the patterns, you find that all these terms, eventually they can summarize into this whole summation. So that's why you can write in this way. I hope this is clear. So when you have, let's say hash tensor 3 times, at this point, you don't need to do all the complicated multiplication. You can just deduce from hash tensor with hash. Of course, if you want to do the hash tensor 3 times, that's up to you. But a more lazier way is to just generalize it by deduction. So that's how you would do it. And you will encounter this again when we go into the quantum algorithm part, which is why I find this interesting. Final thing is on trace. So what is a trace of matrix? Is basically just the summation of your diagonal elements. Over here, there is one trick that I want to show. First of all, we need to know what is a completeness relation. It basically means that um, when you sum all the basis states in this outer form format, it gives you the identity. And you will keep on using this when you want to, for example, write down the matrix elements of uh, a certain matrix, which is what I did over here. So if you have a trace of matrix A, so it is equivalent to identity multiplied with the matrix A and then multiply with the identity matrix again. So over here, I applied the completeness relation. So this is the first one. This is the second one. That's why your summation is in is in J and K. So then you are given the summation of all J's and then summation of all K. In between, you see this kind of thing. So that means that your matrix elements is written as AJK, and uh, that is your outer product for the matrix elements. And this is a summation. So now what trace does is basically trying to impose an inner product. So what trace does is basically something like this. So in the between is your argument. So in between it will be AJK is just some constant, so I can pull it out. The ones that is important is the cat J with the bra J. So they each of them form an inner product. So there's one very clever way to do this. So because they are inner product, so they are basically constant. You can say that. So you can switch the position. So once you switch the position, you find that over here is basically your completeness relations again, right? So then you can just treat this whole thing, removing the I index as your identity matrix, and you will get this inner product. And this inner product is none other than your canonical delta with your index k and j. And if you want to fix to a certain index kj, so you can fix like k equals to j over here, which is why you get the summation of the diagonal elements. So that's how you would show what does a trace of matrix A means in the end. So the trace of a matrix, they satisfy certain properties. First one, when you do the trace of A multiplied with B, so A, B are two matrices, it is equivalent to the trace of B times A. For this one, there's no other way, but you can just test it out with, for example, A11, A12, A21, A22, multiply with B11, B12, B21, B22, and just look at your diagonal elements. You find that if you switch the order from AB to BA, the diagonal elements are the same when you perform this kind of multiplication. So that's how you would prove the first property. So the second property is what we call as the cyclic property. Anyone knows how to prove it? You can unmute yourself and say if you want to. If you can't see it, you can just do trace AB. You consider AB as one matrix, and then you use the first property, AB. And then you slowly do this trick, and you can show that it is indeed fulfilling this cyclic property. So it doesn't work on all the permutations. It only works on the cyclic permutations. So this is the thing that you need to take care of. If it is a addition of two matrices, basically it's just the trace of A plus the trace of B. If you multiply the matrix with some constant C, you can take it out the constant and then do the trace first. If you do the transposition, it is equivalent to the trace of A, mainly because the diagonal element, whatever it is, when you do the transposition, it doesn't change your diagonal elements. So this is another interesting identity. How will you prove it? The way to show this is basically you have trace of A transpose B. So you can extract out transposition B T A. Yeah. So just now when we look at the dagger, just now when we look at the dagger, we find that the dagger operation switch around your matrix. So this switching position of your matrix from AB to BA is not because of your conjugation, it's because of your transposition. So if you have AB, just performing the complex conjugate, you actually get A bar B bar. If you have AB transpose it, you get B transpose A transpose. So similar situation over here. What I did is basically starting from A transpose B, I factor out the transposition. And because I factor out the transposition, you need to switch around the position. So if you multiply the, if you so-called multiply the transposition back, let me write here, BTA transpose. So you first need to switch the position and then add the transposition. So B transpose transpose becomes B. That's how you get back A transpose B. So I hope this step is clear. And then once you did that, this is actually equivalent because of property 5. This is equivalent to B transpose A. That's how you show this. So I start from here, I show here, and then you slowly do the same step again, factor out a transposition, and then deleting out the transposition because of property 5. Eventually, you will reach all the identity as again. The last one, A tensor with B, when you trace it, is equivalent to the multiplication of trace of A with the trace of B. So a very quick way for you to see this is when you look at how the tensor product is being formed. So essentially, you are multiplying A with B when you look at all the diagonal elements. So that's why you have the last property over here. I think the last thing that I want to mention is that if you have uh outer product of psi, and then you have some operator A acting on this thing, so don't care about this thing for now. So what it would become is basically over here. Just now I mentioned that the definition of trace is basically performing the summation I, and then you just do the inner product. In between, just write down your argument. So this is the argument. So after that, right, what I can do is that I switch around the position, and I find that this is the complete relation again, completeness relation again. So I remove this because this is equivalent to identity, and it will become something like this. So this is also important later on. With this, I think I cover pretty much all the stuff that I want to cover for the linear algebra aspect. I think this is quite fast. Uh, yeah. So any questions?
So transpose is commute with the summation.
Sorry, is a bit too soft. Can you speak louder?
So does the transpose is commute with the summation?
Transpose is
Oh, no, sorry,
commute.
sorry, is the trace, trace and also the summation. Like we're taking trace of summation of I AI, then I think from the properties of is that the summation I is equal to summation I
You mean here?
transpose. No, it's below. I think is the third one. I think, yeah, the third one
Oh,
maybe.
this one. Yes, in a sense. Uh, I think I understand why you asked that. The question that you did, right, is a
Okay.
combination of 3 and 4, isn't it?
I
You
uh
also have pi, right?
I okay.
Is it?
Hmm. Let me check.
It's a if you're not mistaken, it's a combination of 3 and 4. So you have to be careful about that.
Okay, okay. Let me check.
The safest way is the reason why I show all this is to show you how the summation and the trace works. Later on I will check your calculation again.
Hmm, hmm.
All right. Uh, Probably I will just stop recording.